We are going to talk about two lectures on estimation. These two lectures are useful because they will tell you how do you actually obtain the Bayesian parameters from the data. Today's lecture we will be focusing on the topic called maximum likelihood estimation. So this is like this is the frequentist approach. And then next lecture we will talk about priors. That will be the Bayesian approach. Both approach, they have pros and cons. And you will see that the Bayesian approach actually has some slight advantage of regularizing the parameters that you will be estimating from the data. It will be extremely useful when you don't have enough observations. But before we go to the Bayesian setting, let's talk about this maximum likelihood estimation problem. I want to show you that given this data sets, and then if this is Gaussian, of course you have already expected that the parameters will just be the sample mean and sample covariance, but I still want to do it more carefully, giving you a more formal framework of how do you extend this idea to distributions beyond Gaussians. Here is the outline of or the roadmap of where we are in this part of the course. Again, we are in this topic called the linear discriminant analysis. We are in the generative method, and we are looking at the Bayesian decision rule. Inside the Bayesian decision rule, we know that we want to find out the model, and then from the model, you want to find out the decision rule, which is a linear classifier. So the outline for today's lecture is that we will go through the basic ideas of maximum likelihood function. I will want to go into more details of a likelihood function, and then what is the meaning of maximum likelihood. I want to illustrate using 1D examples, and then go to general high-dimensional Gaussians. Then I want to talk about estimation problems that are non-Gaussian. I want to show you that this idea is very, very applicable to other problems. And then hopefully we will have time to start to build a bridge from this maximum likelihood estimation to the Bayesian approach, which is called the maximum a posterior estimation. Okay, so what is parameter estimation? The parameter estimation problem can be framed as follows. You have data set. Okay, this data set, you have a lot of data points. And then from this data point, you want to construct a model. And then in our case, of course, it will be a Gaussian model. So you want to estimate the model parameters. In Gaussian, it will be the mu and also the sigma. It will be a vector mu, a covariance matrix sigma. And from there, you can construct the decision boundaries according to what we have learned before. Let's say you have two identical covariance matrices. You know that by using case 1 and case 2 results, you can just draw a straight line classifying between the two classes, right? And so in order to do that, we need to first find out the mu and also the covariance sigma. Because the decision boundaries, the W transpose X plus W0, the W and W0, they depend on the mu and sigma. So we want to find out the mu and sigma. Okay, so this procedure coming from the data to the model parameter is called model parameter estimation. Okay, this is the learning part. If you ask, hey, you're doing this Bayesian decision rule, and then everything depends on the mu and also the covariance sigma, where does the learning come from? The learning actually comes from this parameter estimation. It's a little bit different from the pipeline that we introduced, but you can see that actually when you do this parameter estimation, that involves all the things that we have learned in the pipeline. Okay, so everything goes to this parameter estimation. After the parameter estimation, these can be defined according to what we have learned before. Okay, so I mentioned there are two approaches to do the parameter estimation. We are talking about maximum likelihood estimation in this lecture. Next lecture, we will talk about this map approach. Now, how do you understand the difference between these two? It can be understood by looking at this diagram. This is called a generative process. This is talking about how you can generate the observation from the model. If you follow a frequentist approach or the maximum likelihood estimation approach, what you will assume is that there is an underlying parameter, theta, which defines the distribution, and from that distribution, you're going to draw samples from. Okay, so this model parameter theta, it is a deterministic quantity. Let's say you have a mu, you have a sigma. Once you know the mu, you know the sigma, everything is defined. Okay, and the only problem there is to estimate the mu and sigma. That's the frequentist approach. Now, there's a Bayesian approach which says that this mu and sigma, here I'm denoting by a random variable theta. This theta itself, or the mu and also the covariance, they themselves, they are random variables. And that means behind this generator, there is another generator that generates the parameters. Okay, so there are two levels of generation. First of all, the mean vector comes from certain distribution, and then the covariance matrix comes from certain distribution. You first draw the mean and also the covariance from that distribution, and then you have a generative model, and then you draw your observations from that generative model. So there are two layers of problems. In the frequentist approach, there's nothing called a prior. In the Bayesian approach, there is a prior. Okay. Next lecture, we will talk about the Bayesian, and you see that this prior is actually doing like a regularization type of thing. And if you put the L2 regularization, then you will get a ridge regression type of result. If you put an L1 prior, then you will get the lasso type of regularization. Okay. If you don't put anything, that would be like what we used to see in the traditional ordinary linear regression. So try to map these terminologies into the things that we have gone through so far. Okay. So that's the plan. This lecture we'll talk about this maximum likelihood estimation. Next lecture we'll talk about the Bayesian approach. All right. So let's talk about the maximum likelihood estimation. What do we mean by maximum likelihood, and how do we formulate the problem? So start with a data set D, and this data set contains all the data samples xn and going from 1 to capital N, and we want to ask how to estimate the model parameter. Okay, how do we estimate the model parameter? And we're going to use Gaussian as illustration. Okay, and so we're going to denote theta as the model parameter, and in Gaussian, the theta will contain two quantities. One is the mu vector, the other one is the covariance matrix sigma. And so what is the likelihood given this model? Well, given this model, then you can write the likelihood as this Gaussian equation, because you know that you're working on a Gaussian distribution. You know that the sample is drawn from a Gaussian distribution. As soon as I tell you the mu and also the sigma, that would be the likelihood function. So that's defined. Okay. And so I highlight the fact that the theta here, although I wrote a vertical line here, but this is a deterministic quantity. Okay, it's not a conditional probability. This just says that this is the distribution with theta being my underlying parameter. It's a unknown quantity, but it's fixed. It doesn't have a distribution. It's not random. Okay, so theta doesn't have a distribution. It's fixed but unknown. So, well, then we ask, okay, how do you actually formulate the likelihood? Well, we know that if you have a data set D, that means you have a lot of data points. Then, by assuming that all these data points, they're independently drawn from the data set, which is typically the case, then you can write this likelihood function of the entire data set as the product of all these individual distributions. Okay, so within this product term, these are just the PDF of obtaining the nth training sample. If you take the product, that means you are taking into account of all the training samples in this data set. This is true when all the data samples, they're independent. Now, if you start with this equation, then you know that this is just a simple product, and then the constant term can come out, and so you have the nth power to this constant. Within the exponential, you see that the product becomes a summation. So now you have a summation of all these terms. And I have mentioned before, whenever you do with a Gaussian high-dimensional distribution, you want to look at the negative log likelihood instead of looking at the likelihood, because the negative log likelihood is just a lot easier to handle. So you put a negative log onto this likelihood function, you can get this equation. This is just n over 2 of this quantity. and then n over 2 of this log of 2 pi d. And then when you take the log over the exponential term, then the quadratic term will come out. Okay, so that's just taking the negative log likelihood onto this function here. Now, this hasn't solved the problem. The problem that we have in mind is that suppose I give you the data set, tell me the model parameter. So we need to solve an optimization problem by maximizing this likelihood function. This is why it's called the maximum likelihood estimation, because you want to maximize this likelihood. Okay, so this is defined as the likelihood, right? So you want to find a theta that can maximize this likelihood function. If I substitute this likelihood function by all these product terms, then you can see that you are taking the argmax onto this gigantic quantity. If you put a negative log, and since log is monotonically increasing, putting a negative sign, by solving the maximum problem, you can just turn it into solving a minimum problem. So the max becomes mean. And so what you are having here is that you want to solve this argmean of this entire function that includes both sigma and mu. Okay, so if I can solve this optimization problem, then I'm done. Okay, because by solving this optimization, I have found a pair of mu and sigma that can maximize my likelihood function. Now, you may ask, when will it become different when I have a different training data set? What will it become different? It will be the data points, xn. If you have more training samples, then this n will grow, and these xn's will change. And therefore, the sigma and also the mu that you're obtaining from solving this optimization will become different. So if you have this data set, you have that other data set, because the xn's, they are different, you will have different outcomes. Of course, as n goes to infinity, then you will expect the solution of this mu and sigma, they will converge to the true mu and true sigma. Hopefully that will happen. If that happens, then you say that, hey, I have already found the population mean and the population covariance. Okay, so now let me draw some pictures to illustrate this idea of maximum likelihood before we take the derivative, set it to 0, calculate the solutions. Alright, so how do I understand this maximum likelihood procedure? Assume that you only have a 1D problem with only one sample. Okay, so there are two ones here. The first one is a 1D problem. Instead of two-dimensional Gaussian, it's just 1D Gaussian. Okay, very simple, 1D Gaussian. And then you only have one data point. And you're saying, are you kidding? You only have one data point. How can you do maximum likelihood? Yes, you can still do maximum likelihood with one data point. This is how you do it. Okay, let's write down the equation that you want to maximize. You literally want to maximize this equation of 1 over 2 pi sigma squared exponential of x1, because you only have one data point, right? So you only have one x1, there's no x2, there's no x3, because you only have one data point, minus mu and divided by 2 sigma squared. In this case, I'm assuming your sigma squared is already known, so sigma squared is no longer a variable. You only want to estimate the mu. Okay, so now how do you find the mu that can maximize this quantity? That's very simple, okay? You look at this equation, it's a Gaussian equation. The sigma has nothing to do with your mu, so you can drop that. You can also drop that sigma square. You ask, for what mu that can maximize this exponential term? There's only one solution, which is to make mu equal to x1. If you make that happen, then this will go to 0, and then this will go to, this probability will be maximized. It will be equal to 1. Alright, so, this exponential term will go to 1. Okay, so pictorially what you are doing is this. Let's assume that you have a data point sitting here, okay, and then you have a Gaussian distribution with a known sigma. So the standard deviation is known to you. That's a data point. Okay, so now you're going to move your Gaussian from the left to the right. Slide your window from the left to the right, going from here to there. And then you can ask, let's say I'm picking this Gaussian. Alright, you ask, is this a good Gaussian? By good, I mean that is this Gaussian fitting this data point? And to measure that, you want to see if the likelihood of having this data point coming from this Gaussian is maximized. And clearly it's not, because the likelihood to get this blue point from this black curve is not maximized, since the blue dot appears at the tail of the black curve. That probability is not maximized. That likelihood is not maximized. So you say that this black curve is not a good curve. I am going to shift to the left, okay, to the right by a lot. So you go to here and you say that, is this a good curve? No, again, it's not a good curve, because the likelihood of getting a blue dot from this black curve is even worse, right? So now you shift to the left again, and then gradually you find this red curve. You find this red curve, you ask, is the probability of getting this blue dot from the red curve the highest? And yes, it is indeed, because the blue dot is centered at the middle of your red curve, and so the likelihood is maximized. That explains the meaning of maximum likelihood estimation, because you want to find a distribution that can maximize the probability of getting that data point. Okay? You don't have to go to the equation. Just look at this diagram. You know that what's going on in this maximum likelihood estimation. Now, let's also do another exercise by thinking about how about I have two data points, okay? So now you have red dot 1, blue dot 1, blue dot 2. You have these two data points. You start with a distribution which is this one, and you ask, is this a good distribution for these two data points? Or what is the likelihood of drawing these two data points simultaneously from this black curve? It's a very bad guy, because this blue dot comes from the tail, this even comes from an even worse tail. So the probability of getting these two dots simultaneously from this black curve is bad. All right? Then you move around, you find that, okay, in the middle, this is the right curve. And what is this curve? Well, even without looking at the equation, you know that the center has to be the midpoint between the two blue dots. Is it the case? You go to the equation, you verify that, you take the maximum likelihood estimate, and then you write down these 2 points. You solve this minimization problem. It's indeed x1 plus x2 divided by 2. Okay? So there's no need to go to the equation. By just looking at the diagram, you know what you're doing. Now, let's work on more complicated examples. When you go to arbitrary n, of course this is harder, but the same principle applies. You're moving your Gaussian left and right so that all these data points, they will simultaneously be likely to happen, right? You cannot just say that, okay, I'm going to maximize one point but not the other point, because this entire problem says that what is the likelihood of getting all these data points simultaneously? So the only way to make this happen is to shift the red curve in the right place, such that the chance of getting all these is maximized. So if you go to the equation, then you can realize that the maximum likelihood function becomes the maximum of this negative thing, right? And so you can bring this negative exponential term by putting a negative log. Then you have this minimization of this quadratic term, and you do some linear algebra. Then you can show that the mu would be just the 1 over n with the summation of all the samples. Okay. Now, how to do this? This equation is fairly simple. So you take the derivative with respect to mu of this guy, making it to 0. And then do some very interesting linear algebra, you can get this equation. Okay, it's not too hard. Okay, you can see that this is a scalar, and so taking the derivative should be pretty easy. Okay, so that's the idea of maximum likelihood. Okay, it's nothing more complicated than finding a curve that fits best to the data points, and now you can extrapolate this idea to very high dimensional data. So suppose you have data points here. Okay, so I ask, can you find me the maximum likelihood estimate using a Gaussian model? Then what you're doing is that you're going to draw a Gaussian. Is it here? Is it here? And then eventually find this Gaussian is the best. What you're doing? Well, because what you're doing is moving this circle or ellipse left and right, up and down until a point that the probability of getting all these data points is maximized. So how do you solve this problem? Again, let's assume that your sigma covariance matrix is fixed, is known, so you don't need to worry about that. Then you just need to estimate the mu. In that case, you can just write down this arc mean of the negative log likelihood function. It will be a function of this quadratic term. Now, if you take the derivative of this quadratic equation, right? So you take the derivative of this quadratic equation with respect to mu, then you can get this equation here. Okay, I'm skipping some of the steps. So you can get to this equation here, and once you get to this equation here, you can move the terms around, and you can show the following. You can show that the equation will lead you to this expression. The summation of all the data points xn will equal to the summation of the mu, and this is nothing but just n times the mu. Right? Because all the mu's, they are the same for all these summations. So the n times the mu, and therefore you have the solution of mu equals to 1 over n times this summation of all the samples. Okay? Again, this is very easy. If you are working on a Gaussian, you do not need to go through all these complicated derivations, right? You know that since it is Gaussian, I know that the mean has to be the sample mean. What I do is just that I take all the data points, calculate the sample mean. It's very easy. One line in Python, okay? What is the covariance matrix? Sample covariance matrix. Another line in Python, right? But the reason that we are going through all these derivations is show you that there's a reason behind of doing all these, because the sample mean and also the sample covariance, they are indeed the guys who maximize the likelihood. And that's the reason behind of all these calculations. Okay, so what you have found is called the empirical average of the data set. This empirical average, by definition, it is the sum of all these random vectors. Okay, therefore, this mu hat itself is a random vector. Okay, it's a little bit confusing, right? So now let me say it again. All these xn's, they are random vectors, and therefore, when you take the average itself is a random vector. Therefore, the random vector mu hat, it has its own distribution, it has its own mean, it has its own covariance. All right? Okay? This guy is a random vector, and therefore it has distribution, it has means, it has variance. You can show that the expectation of this guy is mu, the xn is mu. Therefore, you can also show that the expectation of mu hat is also mu. Okay? Okay. Make sure you understand. Mu hat is not mu. Mu hat is the empirical average. The average of this average is the true average. Isn't it confusing? Okay, that's very confusing. But that's unfortunately the truth. Okay? This is a empirical average. If you take the average, if you take the expectation of this empirical average, you will get a true mean. All right? This itself is a random variable. It's not a deterministic quantity. This mu is a deterministic quantity. They are different. Okay? This you have random fluctuations. This one, you do not have random fluctuations. Okay? I want to make it very, very clear, because that will play a very important role when we try to quantify how well does your learning algorithm perform when I only have 20 samples versus I have 5,000 samples, because the number of samples will affect the quality of your mu hat. The number of samples will not affect the ultimate quantity mu. The mu is still there. That is the ground truth mu. That is a deterministic quantity. The number of samples will only affect your mu hat. Okay? So if you have a bad mu hat based on the finite number of samples, then that is something that you need to quantify. You need to quantify the performance span of your estimate. Okay, so we say that mu hat is an unbiased estimator of mu because we have just shown that if you take the expectation of mu hat, you will get mu. Okay, so if this happens, we say that mu hat is an unbiased estimator. Now, if both mu and sigmas are unknown, then you have a little bit more interesting game to play with. Then you need to take the derivative with respect to mu and with respect to sigma simultaneously. and I want to highlight this word. It's not a very welcome word, but it's doable. It's just a little bit more tedious. And then if you do that, then you can show that the mean vector mu hat will equal to this sample mean, and then the covariance matrix will equal to this empirical covariance matrix. Okay, and now the high dimensional proof would be tedious. However, in the 1D case, that's pretty straightforward. I will actually encourage you to take a look. This is not hard to prove. Meaning that if you set the dimensionality of xn equals to 1, that becomes a scalar. That becomes a scalar. So you just estimating the variance rather than the covariance matrix. Finding these two equations should be pretty doable. Okay, so you can do it at home. Any questions so far? Yes.
So what if you can't use a Gaussian data? You can't get the closest distribution that.
Okay, so the question is, what if your underlying distribution is not Gaussian? All right. So now you're asking a very interesting question. That is, what if my underlying model does not meet the model that I'm using to do the inference? There's a price you need to pay, which is called the model mismatch. All right. If you have that model mismatch, then the price you need to pay is during the generalization, during your testing. Because by testing, I mean that there will be sample coming from this true distribution, which is not Gaussian. Then since you're using a Gaussian to model that, the decision boundary will cause some error. Okay. Now, will it really always cause error? That's not always true. As I have shown you in the previous lecture, that if your true distribution, they are isolated. Okay, they're uniformly bounded in two different clusters. And then you're using a Gaussian to find that classifier. It won't cause any problem because they're intrinsically not overlapping. Okay, but in general, the two classes, they're overlapping. They may have a non-Gaussian distribution. And then since you're using Gaussian distribution, that would be the thing that that would be the price you need to pay. Now, there's a second level of error, which is, even if your underlying model is indeed Gaussian, however, you do not have enough samples. Okay, you only have 5,000 samples to estimate your mean vector and your covariance matrix. Then that is another level of price you need to pay. Okay, compared to someone who has 10 million data samples. Okay, this is like a typical comparison between university and company, right? So when they have a lot more data samples, then of course their estimate will be a lot better than yours. Okay, that has nothing to do with intrinsic distribution. That has something to do with the complexity of your sample, right? So then there are different issues here, and I want everyone to just to tune up your mind that whenever you see a problem, it's not obvious which one it comes from. Okay, be very clear whether it comes from the finite sample problem or does it come from the intrinsic distribution problem. If it's the intrinsic distribution problem, you may want to work harder to find out the better model. If this is the sample problem, go ahead and collect more data samples. Okay? If you cannot collect more data samples, then you may want to do some regularization to estimate the model parameters more carefully, perhaps using Bayesian approaches. Question?
So what would be the difference between the outcome of this, the MLE and the experimental result we got just from all this data sample? Just we try to find out the mean value and the covariance value. Will there be any difference between them?
Okay, so the question is, what is the difference between the thing that we are doing here, theoretically, versus if I really just download a data set, I calculate sample mean and sample covariance. Okay? In the finite sample case, they are exactly the same. In the finite sample case, they're exactly the same. Okay? But what I'm showing you here is that, in the Gaussian situation, okay, this sample mean, okay, let me put it this way. The sample mean that you're calculating from the data set, the thing that you would typically do in practice without knowing this lecture, is indeed optimum with respect to the likelihood function. Okay, so I'm giving you a justification of why you should do this in practice. All right. Now, when will they become different? They will become different when my number of training samples goes to infinity. Okay. Now, I wouldn't say that it's different It's just that when my training samples goes to infinity, then you can see that this equation here, this equation, this thing, it will gradually converge to the expectation of the true underlying model. Okay? So if indeed the true underlying model is Gaussian, then my mu hat will converge to the true mu hat. However, if the underlying distribution for this xn is not Gaussian, and if I'm doing this, then I will converge to something that is not the underlying true distribution of that distribution. You see the difference? So let's say the underlying distribution is Laplace. All right, and then Laplace is not a very good example. Maybe some Stanley distribution. Okay, some distribution that is not according to this formulation. All right, so some distribution, and then you take the sample mean, you calculate that. Okay, even if you have infinitely number of samples, the sample mean that you're calculating will not converge to the sample mean, to the true mean of my distribution. Okay, because my distribution has a crazy mean. Okay, if I am indeed a Gaussian, then you're in good shape. This lecture gives you all the theory that can guarantee you that you will converge to the true distribution. So just be careful between the underlying model and also the number of training samples. Okay, it's the same question here. More questions? Yes.
For the covariant estimator, when would you choose a biased estimator versus unbiased? Because covariance can be defined.
Okay, very good question. So the equation here I'm showing you here is called a biased estimator of the covariance matrix. When do you want to choose an unbiased estimator? That's debatable. Okay. Practically, I can only speak from my experience. There's no difference. Okay. The reason is the typical problems that at least I'm encountering is n equals to at least 1 million. N minus 1 versus n, that difference is just negligible to me. Now, you need to worry about that when your n is small. Okay? When n is small, then n versus n minus 1 will give you a different result. Okay? Now, what is the implication of that towards your decision boundary? That is something that unclear. Okay? At least I haven't really studied that problem yet. I would just say in general, most of the problems, if you're in the computer vision domain, natural language domain, this is not the issue you need to worry about. The issue that you really need to worry about is that because you're running maximum likelihood, the parameter you are getting there may not be that good. In particular, your underlying distribution doesn't match with your true distribution, match with your inference model. Okay? And therefore, you may want to use regularization terms to put into priors so that you can get a better estimate. So that will be the bigger question we ask. Okay? I will come back to this point later, talking about what do I mean by biased versus unbiased covariance. But thanks for bringing this up.